I'll be talking about introduction to data science for geoscientists. It's a very interesting topic. Everybody's talking about data science. Everybody's talking about machine learning. Today we'll be introducing you to what data science is and how you can use this as a geoscientist. At the end of this presentation or this short course, the participants will understand the following things. First of all, they will have a grasp of what data science concept is and definition of terms. There are different terms associated with data science analysis. So I'm going to be defining all the terms so that you have understanding of what they are and how they all relate. Also, data jobs, talk about the different jobs within the data science space. Also, talk about the data workflow, data science workflow. So if you want to do data analysis, where do you start from? How do you progress through? Then also then we start bringing it home to geoscientists, because majority of us here, we are geoscientists. So talk about, okay, how does data science, what's the role of data science in geoscience? Then we cannot start talking about specific applications of data science in geoscience. Then we'll also talk about the tools. So if you want to do this, what are the tools you should look out for? What are the tools you should be learning? Then also talk about some other skills because within data science, it's not only about the technical skills, there are other soft skills that is also required. Okay, then we'll talk about the roadmap. So if you want to begin, where do you start from? Where do you go? And how do you start? So we'll just be covering everything in the session today. And I hope that sounds exciting. So let's kick off with the first, what's data science? The first is data science. Data science is the use of scientific analysis or statistics and your knowledge of programming to gain insight in your data or about your data. That's just like a summary of what data science is. And as a subset of data science, we have data analytics. Data analytics is the science of examining your data to come up with useful trends and come up with or to make actionable insights. So it's looking for trends and patterns in your data in order to drive decision making within an organization. So also just know that data analytics is a subset of data science. Data science is a broader field. On the other hand, we have artificial intelligence, which typically involves using technology or training machines to interpret information just like a human would do. And there are overlaps. You see, there are some overlaps between artificial intelligence and data science. So they are different, but you have some overlaps within these two fields. As a subset of artificial intelligence, you have machine learning. Machine learning is science of teaching machines to do things the way a human would do. So for example, if you have a child, you teach a child how to sit, how to stand. So machine learning is about training your computer to do things that you would normally do, and they have the ability to kind of identify patterns within your data. And there are different types of machine learning. There is the supervised machine learning, there's unsupervised, and there is reinforcement learning. I realized that there's another session for machine learning. We don't really talk about machine learning, but I just thought to mention because it also is included within the data science workflow and the data science job descriptions. Then a subset of machine learning is deep learning. So this uses like the way you have neurons within your brain. Same thing, your deep learning works. It has neural network, so it's a kind of a subset of machine learning. Is deeper where you have to train different models or using different neural networks in order to make predictions. Then we also have what we call data mining. Data mining is a different paper. As you can see from the diagram, it cuts across different things. So you have it in data science, you have machine learning, so it cuts across these different fields, and it's the process of extracting valuable information from your data, from big data. So some people confuse data mining from within data mining and data analytics. They are different. Data mining is focusing on extracting valuable information, while data analytics, you are identifying trends and patterns. You are analyzing data to come up with trends and patterns within your data. Okay, then we have data engineering. These are different terms you start hearing when you start talking about data science and data analysis. Data engineering focuses on looking after databases, data warehouse, that's making data available for a data scientist or a data analyst to work with. So when you talk about database management system, they are the custodians of database. They build, manage, and maintain database. so that the data scientists, data analysts, or machine learning engineers can pick up this data and utilize it. So we see in more details how this all where they come in within the workflow and what they do within the data workflow. Then at the center of everything we've talked about is big data. Big data is, as the name implies, are data that are very large. They are big, too big to fit into our computer. So I'll explain more of that later. But if you notice, everything we've talked about, it's all centered around data. You get data analysis, data science, data engineering. The focal point there is data. So now I want to start asking ourselves, what is data? Simply put, data is information. According to Cambridge Dictionary, I'll just read from the screen. Data is information, especially facts or numbers, collected to be examined and considered and used to help decision making or information in an electronic form that can be stored and used by a computer. That's like a long mouthful, but in simple terms, according to the American Dictionary, data is information collected for use. So any useful information, you would consider that as data. It could be as small as anything, as long as that information is useful, you can consider that as data. And there are different types of data depending on your industry, where you work, or whatever you do. So for example, there is geographical data, there is geologic data, there is transport data, there is financial data. So within different industries, they acquire data differently. So you have data, this kind of data. Then there are two forms of data. So we have we have the traditional data. We also have the big data. So what you consider traditional data are data in megabytes or gigabytes. So any data that you would normally use, so data you have in your computer, used for doing analysis, your spreadsheet, those are all traditional data. But when you start looking at big data, these are the data that you can't even fit into your computer. They're in the ranges of petabytes of data. So I will give you more explanation on what are the characteristics of a big data. So I just explained that. Structured data. Okay, now let's talk about big data. Like I mentioned earlier, big data are data in petabytes, so they are too big to fit into your traditional computer or what your PC or anything you use. So, and big data is, aside the fact that it's big, it's also characterized by 5 V's. So before you can call something a big data, it must possess these 5 V's. So the first is volume. Definitely it has to have a large volume. It has to be big and massive in size. Then the next V is variety. The next V is variety. That's the nature of the data, the type of the data, where the data is coming from. Are they coming from different domains, different skills in like the world today? We're talking about data. For example, we could talk about social media likes, social media comment, things that, like, when you see that they are coming from, you could have them in different formats. That's what variety relates to. Then we have velocity. Velocity has to be coming in real time. So if a celebrity on social media puts a post today, you see comments coming in like in real time. In oil and gas, you can liken that to, for example, logging while drilling, production data, or so when you have a field and you're producing oil and gas, so you see data generated in real time. So it has to come in real time and it has to have velocity. Then the next thing is veracity. It has to be from a trustworthy source. Like you have to, the data has to be reliable. You shouldn't be something that where it begs for what's the how trustworthy is the data. So you have to make sure that the data is from a reliable source and it's not giving you false information. Then the last V is value. So you don't want to waste you don't want to waste time storing information that is not useful, because like I said, large data and big data, they are large in volume. So for you to want to get to that data, it has to be important and it has to be useful. It has to be valuable to whoever is using it. Then we talk about data forms. There are different forms of data, right? So first of all, we have structured data and unstructured data. So what would you consider structured data? These are data that are in a definite pattern, and yeah, for example, an example of a structured data. I don't know if you've worked with Excel before. Have you seen Excel data where you have rows and columns? They are in a structured format. You can easily search and extract data. So that's what we consider those kind of data. They're in rows and columns, structured data. On the other hand, we have unstructured data. So everything that is not structured. So everything that is not involved in what I've classified as like tables and columns, there are unstructured data. This could come in form like video, audio, social media posts. It could be from images, PDFs. All those are all classified as unstructured data. So what structured data is straight to the point, is factual, is well organized. So if you want to carry out your research, you want to do analysis on data, you want to go, you have to use a structured data to carry out, to do your analysis. Or on the other hand, unstructured data are usually qualitative, not quantitative. So it has to go through a process to convert that data from unstructured to structured before you can start analyzing or you're doing any of the data analysis process or methods. And usually unstructured data requires a lot of storage spaces because they are usually kind of, the file sizes are usually large. Okay, so this is just like an example. When you talk about structured data, it's well organized. Unstructured data is everything. You have everything thrown in there, scattered. It's all disorganized. So I think this pictorial representation would give you a mental picture when you think about structured and unstructured data. So in summary, structured data are tabular data in CSV, Excel files, and they are easy to work with and they have less storage space. Unstructured data is every other thing, and you have to work through to process this data into a structured format before you can start analyzing the data. Okay, now let's talk about data science. We've talked about different terminologies. Now let's talk about data science. Data science combines scientific analysis, your scientific analysis, like the data analysis in itself, statistical knowledge. So you have to have a good understanding of statistics, computer programming, and also domain expertise to analyze your data. So for example, if you want to, as a data scientist, you can work in anywhere, but you also have to have understanding of the domain you're working with. You have to have a good understanding of the data. For example, you're working with a geology data. There is so much a data scientist that's not a geologist that or doesn't have knowledge of geoscience would do with the data. Or if you're working in a financial industry or in investment banking, you have to have an understanding of investment. You have to interpret the data. So there's a limit to what you can do applying regular data science techniques or skills. But if you have the domain expertise, it's an added advantage. So rather than, my point is, if you want to become a data scientist, you have to bring everything together. It's everything fitting together. It's domain knowledge, it's programming, it's statistics, it's mathematics, it's machine learning, it's knowledge of database. So it's like you have to have a combination of skills to function well as a data scientist. Then there are different phases in data analysis. When you want to start data analytics, there are different phases you have to go through. So I'll just classify this based on your value. I'll just show you how it differs based on as complexity and value increases. So the first stage is descriptive analysis. So this is about what has happened to the data. So if you have a data, you want to kind of more like diagnose what's like descriptive, what has happened previously with the data, what phases has the data gone through. So that's descriptive. Then you have diagnostic analysis. So if you understand what happened to the data, so what's the data telling you? For example, if you have, let's say, a data of, let's say, geologic information, you want to understand, okay, what before I acquire this data, what processes has this, let's say, rock gone through to before I discovered it. Then you want to diagnose why did it happen. So if you say it happened this way, what are the reasons that this resulted in it happening? So from there you can now start predicting. Like geology will say the present is the key to the past. So in this case, if you understand the past, you can now start predicting the future. So if I understand that XYZ happened before, then I can say, okay, if XYZ happened this way, then I can now make prediction based on the previous occurrences. Okay, then we have prescriptive. So if you've understood, okay, what has happened, why did it happen, what will happen next. So if it's, for example, how do you influence what will happen? So if your prediction is great, so how do you kind of influence it? Do you want it to happen faster, quicker, or if it's going to be a negative prediction, or if it's a negative prediction, so how do you prevent that from happening? So I think there are the 4 different stages of data analytics, and you have to go through the 4 different stages whenever you're doing your analysis. So this is just shows a summary. So you have the insight, you have insight, and you have the foresights. Okay, we've talked about all this. Now let's talk about different, when you talk about data science, data analysis, there are different roles. Like when people come into data science, one of the kind of frustrations I get. They just feel like I just want to become a data scientist. They don't understand the landscape, understand where you fit. So you have to understand, okay, what are the different roles? What do they do? So you can understand, okay, how do I come in? Where do I fit in? First of all, we have a data strategist. These are people that understand the business, understand, okay, what do I want to do? So they understand all kind of data. So if you understand the business, understanding what the problem is, they can now start thinking about what kind of data do we need to answer our questions or answer the questions of the business. Then we also have a data architect and also a data engineer. In most cases, some of these roles they overlap. Some you have the same person doing two different roles, but ideally most of these roles are different. For example, you have the data architect and the data engineer. The data architect will kind of construct or derive database structures. How do we want our database to be? What are schemas? What are these? What are that? And the data engineer would now be in charge of building the database, building the data structure, just as suggested by the data architect. But in most cases, they overlap, so you don't really have that. They also have a data analyst. Data analyst, based on the data that data engineer had developed, the data analyst can now query the database to get data to analyze and come up with insights. A business analyst, on the other hand, understands the business. So they use using the business objectives. They can also analyze, okay, where are the places where we can where are the places where we can improve the business to make better decisions. And we also have a data scientist that does does the role of also a data analyst, but also goes further. So if you want to compare, like looking at a data analyst and a data scientist, because most time people confuse the both of them. You see a data scientist, see a data analyst as someone that also, if you see a picture, let's say you go to, let's say Abuja, for example, and you just take a picture of a building, you can analyze that building deep, analyze the roofing, everything about the building. But a data scientist will come and look at the whole landscape. So now it's not only looking at the building, it's looking at around the surrounding building, it's looking at around the vegetation, it's looking at the sky, it's looking at everything around that area. So data analysts are kind of zoomed into a particular area, but data scientists also like look at the broader picture. Data scientists also do predictions. So if you are seeing a bigger picture, you are able to better make predictions using machine learning and other technologies. They also have machine learning engineers and machine learning operations, ML ops engineers. So in most cases, these roles can overlap. So you can see one person doing data scientist, machine learning engineer, and also machine learning operations engineers. In some cases, they are all over. The same person can do them, but in some cases, you have them as different distinct roles. Okay, then let's just talk about data science job roles. Like I just kind of picked out 4 main roles I mentioned, so you can take a snapshot of this. I wouldn't be going through all of them, but what I'll be focused on is, for example, a data engineer. I told you they manage databases, they build databases, they use SQL or no SQL to manage databases. A data analyst looks at some of the programming, so they clean the data, analyze the data. For example, you see that data analysts use SQL. A data scientist, you will also use SQL, but they use it differently. For example, a data engineer would use SQL to build database and manage the database, but a data analyst and a data scientist will use SQL to query the data. So they don't necessarily need to know how to build database or how to manage database. You can do, but they don't necessarily need to. What they are focused on is how to query the database. So if, for example, you are a manager in a warehouse, you know that, okay, they store XYZ, you're not bothered on how they are stored. All you know is, okay, if I want to pull out some goods from the warehouse, I know how to pull out the goods I want to use. So that's why you shouldn't have people going to learn these different tools or learn different tools, because they don't really need it in case. So you have to know what role do I want to play. So you are focused on the role you want to apply for, or the role the skills or the tools you want to use to achieve your purpose. Then we have the machine learning engineer that focuses on using training models, building predictive model, using classification, regression, or deep learning algorithms. So for example, a data analyst, you don't really need Python or R. You could just use Excel, Power BI, Tableau. But for a data scientist, because you are also going to start making predictions, you want to, okay, yes, use it's good to know all these tools, but you also have to know a programming language, Python or R, depending on your organization or what they use. And some of these are, if you look at the bottom, you see like some tools or libraries that these different roles they use. So you want to read that. So in summary, a data engineer stores and look after your data. A data analyst visualizes and describes your data. Data scientist gains insight from your data, and a machine learning engineer makes predictions. So if you have questions, please put in the comment section. After the presentation, I would answer your questions. So let's talk about workflow. When we talk about workflow, it starts from what's the problem that wants to be solved. So you have to identify the problems to be solved. Then you start thinking about, okay, what data is available. So that's where a data architect, a data engineer will come in, what data is available. Then you have to go through data cleaning. That's where you start looking at data scientists or a data analyst. So you get data that is available, you clean the data to suit what you want to do. Then you start doing exploratory data analysis. So you want to look at what is contained in your data. What do I have? What insights can I get? Then you can now start doing data transformation. So after you understand your data, you can now start transforming the data to prepare it for machine learning or making predictions. Then after your data transformation, this is where prediction begins. So for example, a data analyst will focus on data cleaning and EDA. That's the gray and the green circle. Then a data scientist will pick it up from there and continue with data transformation, because you want to start training the data, preparing the data for predictions, right? Then from data transformation, you start training your models, making predictions. Then you evaluate your model. When you train your machine learning model, you want to evaluate your model. In some cases, the model might be right. In some cases, you need to. So when you have like a not a favorable result, you either retrain the model until you get good results. In some cases, retraining the model wouldn't be good, so you have to go back to the data to get more data or get a different kind of data. Or in some cases, you have to revise the problem. So if you don't have enough data to answer the problem you have, or to answer the questions you have to maybe revise your problem statement in order to fit the data you have or acquire more data, things like that. Then just know that sometimes these processes could be iterative. So you go through in loops and come back, things like that. Then when your model is good to go, then you deploy your model for whatever, for applications. You start looking at software engineers and other things like that. But I think that's just like a general summary of how the data science process and workflow goes. So I'll just kick off now. So the first part was me talking about generally about data science, the workflow, the different roles. Now I'll be bringing it back home, seeing its applications in geoscience. So before we talk about data science in geoscience, what's geoscience? I know we all know this, but just for the sake of the 1% of people that might not really know what geoscience is, I'll just say geoscience is also known as earth science. So it's the study of the earth, including its structure, the processes that led to the formation, and also mineral deposit within the earth. You have different disciplines in geoscience. You have geology, you have geochemistry, you have metrology, environmental science, palynology, sedimentology. There are a lot of other sub-disciplines within geosciences. And a big goal of a geoscientist is discovering different processes within the earth. Like I said earlier, also discovering minerals, like discovering oil and gas, discovering other transition elements or other energy resource within the earth subsurface. And we'll see how geoscience can help you, or how data science can help you achieve these different goals of as a geologist. So let's just talk about data transformation. It's a technology that is being used across many industries. Even in geoscience and earth science, we are not left behind. We're already adapting this technological advancement in whatever we do. For example, before now, many years ago, seismic interpretation, for example, was done manually using paper, but we progressed to using digital, using things like Petrel, OpenWorks, and Decision Space to analyze do our seismic analysis. But now things have evolved, and we're even now using artificial intelligence to automatically identify some of these structures and do some of the things we already do normally using our traditional technologies. So now let's start talking about, okay, what role a a data scientist play in geoscience? First of all, you can automate. There are lots of tasks within as a geoscientist that you do daily that you can automate. So rather than doing the same thing over and over again, you start thinking of, how do I automate this process? How do I make this process efficient? Okay, and you can also help you predictive modeling. So if you have your data, you can usually predict, okay, what's going to happen next based on the data I have. That's where predictive modeling comes in. Then you could also use it to enhance your mapping. For example, you have seismic images. You can use machine learning models or data science techniques to enhance the quality of your data, of your seismic, of your core data, or your thin sections, for example. You could also optimize your data. So in subsequent slide, I will show you examples of these different processes. For example, data optimization. Within the industry, we have a lot of legacy data trapped in old formats, maybe previous formats that were used to store data that's no longer being useful. With data science techniques, you can extract data from this information, and I'll show you some examples. You could also reduce complexity within your data, because when you start training models, when you start doing principal component analysis, where you could have multiple dimensions of data, but with these technologies you can reduce that dimension and also gain more insights from your data, because you are looking at different kind of data in different complexity. So it's being reduced, but the value in the data is not being lost. Then it can also lead to new discoveries, because most of these things are done using different mathematical these things, are some patterns that might not be visible with the natural eye, or if you're using the traditional technology. When you do use data science, you can now start spotting trends, patterns, or even some of these patterns or abnormally are usually associated to new discoveries. So with these technologies, you can make new discoveries that you would naturally or normally not make with your traditional methods. So in summary, it can help you save time, save labor and cost. So for example, the time you use, so an example of this is my as during my MSc, I trained a model to predict lithologies from well logs, and I worked with over 100 wells, and based on the model, in less than 15 minutes you can get your predictions. But traditionally, if you needed to interpret those words, it could take you over a month to interpret those wells. But in less than a day, you see that it has improved. So if you needed like 10 people to do that job, you need less than one person to do that. Also eliminates eliminates human error or biases. Like for example, differentiating between dolomite and limestone can be quite challenging. Some of people make this interpretation based on their personal biases. So if you're introducing data science, some of these biases can be eliminated, because you're following some kind of principles, and also helps you. So rather than focus on doing things like initially I mentioned, like what a job of 10 people, you have one person do it. It does not mean those other people are going to lose their jobs. It just means they are focused on more productive things. So if you look at the red text within at the bottom of my screen, say data science or machine learning does not pose as a replacement for geoscientists, but in the hands of the right geoscientist, a powerful tool can make improvement. So rather than focus on things that a machine can do, it helps you apply your brain to more technical and more productive things. Okay, so now let's talk about applications in geoscience. Some of the applications where you can apply geoscience, you can apply it in climate and meteorology. You could also for environment and resource management. So for example, climate and meteorology, you want to understand, let's say, climate, the weather condition. You can pick up data, analyze the data, and also make forecasts based on that. So if you look at all predictions, so if you pick up your phone, for example, and say you're predicting or forecasting for weather conditions or climate, most of these things are done with data science. It's not just somebody said. So technology can help you improve that processes. Then environment and resource management. So if you look at for example, landslide, earthquake, if you get the right data with data analysis or data science techniques, you can identify areas where you can, for example, your water resource management, or where a natural disaster would happen, and how to prevent such. You can use it for mining and mineral exploration. So where you do your mining, For example, it can help you predict where a location of a mine or mineral deposit, things like that. And it can also help you in exploration of, let's say, oil and gas resources, do 3D structural models. So let's talk about some examples of applications. For seismic, for example, you can use data science to predict do your structural interpretation. So where you have fault, where you have salt domes, it can help you identify these fault areas where, okay, these areas are, you have inconsistency, things like that, or find where you see structural configuration. You can train models to automatically help you interpret your seismic, to help you interpret faults and structures, things like that. It can also help you in improving your seismic processing, so improving your seismic quality. You can train models, some neural networks, to help you process your seismic and to get better image visualization from that. You can also, so I talked about fault interpretation, I talked about seismic processing. You can also talk about horizon interpretation, so track an horizon across different seismic lines and seismic lines and seismic cubes. Then you could also do seismic facies analysis using data science. So if you see the images on your screen, these are examples of how this has been done using seismic. So these are all images from using seismic to identify different things. So for example, you see how data science and Python, using Python programming, they've been able to identify, like, this is an amplitude map, this is a Fourier transform map, and this is also a Fourier map. You can see how you've been able to analyze different facies within a seismic cube using Python and data analysis techniques. Down here, you can see from a seismic image how they've been able to apply clustering. This will be an unsupervised machine learning to identify different clusters, and these different clusters can be associated with different facies. So when you do this across multiple lines, you can now get like your seismic cube or your surface of different structural or facie changes as you move along. And this is just shows, this other one, it just shows alluvia, how you have been able to identify some fluvial channel deposit within a region. All this using seismic, so without using traditional softwares that you normally pay for. And most times, so Python, for example, data analysis tools mostly are open source, so you don't have to pay to do all these things using machine learning or using your Python programming. For example, it's free to use. Just pick up your computer, know what to do, and you can start generating all this without paying subscriptions. Okay, let's move on to well logs. Some examples, some applications of data analysis in well logs. So you could use it for petrophysical evaluation. So you have your well logs. So some of those analysis you will normally do as a petrophysicist, you can apply those calculations. So if in this case of here, you see your neutron gamma ray resistivity, neutron density. So you have they've calculated for effective porosity, Archie's water saturation, calculate for the water saturation, and in this case you can also identify different formations using and displaying like this. I plan to start a series on my YouTube channel coming shortly that will be data science applications in geoscience, and I plan to start with well logs, and from there we'll move on to seismic. So if you're really interested in things like that, you can register or subscribe to my channel so that you are updated when I drop this content. In other cases, you can also improve. So in some cases where you, for example, if you have core data where you collected core samples, so for example, when you get core data samples, you can get porosity and permeability from your core samples. In most cases, these core samples are discrete, they're not continuous. You could just be at different depths. With ML, you can train models to kind of extrapolate and kind of predict a continuous curve for porosity or permeability based on the samples you've gotten. You can, as you can see, in these cases, you can also do, in this case, you can also do well log correlation using ML, automatically correlating between wells. So there are different machine learning models. So whenever I talk about data science, it also includes machine learning. You can't really separate them from the self. They also do prediction. So this is an example of my project work where you have wells and you predict based on that. So you apply machine learning. In this case, you see how it's doing good prediction, predicting the right lithologies based on the input. Then you can also predict for petrophysical properties like water saturation. You can make prediction based on water saturation. You could do for porosity. You could do different. Just talk about. So one thing I tell people is, whatever you do, whatever you are doing, if you're already working or you're doing your project, for example, whatever you can do using the traditional method, you can start thinking about how can machine learning or how can data science be used to improve that process or used to make that process more efficient mainly. So in this case, they've used it to predict for petrophysical properties. Okay. And in other cases, so the next one I want to talk about is thin sections or core images. In some cases, you as geoscientists will work with thin sections or core images. So for example, for thin sections, in this case, you can use ML model, use like this SAM model, segment or anything model, to identify different properties within your thin section. For example, you want to identify the clastic, or for example, you can also get porosity from your data. In this case, for example, if you say the blue represents things like water, for example, you can use this to calculate the percentage of where you have your pore spaces, for example, within that coin. It can help you identify porosity, or it can help you identify the different items or different fascies you have within your core, your thin section. In these other cases, they've used it to identify the different using machine learning to identify the different class within the thin sections. You want to see, is it calcite, you have quartz, dolomite, things like that. So if with a detailed thin section analysis, there's so many information you can do, and this can be done automated. This can be automated, and you don't have to spend time trying to do this manually, because you just train models. Whenever you feed in that, it already identifies the different segments within your image. You can also use it for core analysis. So this is an example of you're given the score. So in some cases, the core we're missing. So if you can train the models, in this case, say the model that has been the result of the model, so you've been able to identify that the blue, for example, are areas where you have empty core. So you can easily just predict, okay, within this depth and this depth. So, and each core had like a depth interval. So if you are able to train a good model, you can say, okay, within this depth to this depth, I'm missing data, or this is where we have data. You can also splice them together. So you see them at different rates. You can also, with your model, you can stack them, so you have a continuous core core log. And also, for example, in some cases, you might have picked out, let's say, taking out plugs from your core depths. Your model can also identify the depths where those core were taken. So you already have things automated, and you can extract. So for example, this is an example of like an unstructured data. But if you go through this ML process, you can turn this unstructured data into a structured data. For example, you get the depth. You can also, in some cases, you can also train your model to see the lithologies. So for example, to see the different lithologies along your core. So those information can then be transformed into a structured format, and you can start carrying out analysis based on this. So this is also an example of a core data where we've done fascia analysis, and all these things were done using machine learning, using data science to predict the lithology. So you don't have to go start looking at, okay, somebody say, oh no, this is a shale, no, this somebody else will say this is a shelly sand. But if you're able to train good models, they can identify and pick at least those little differences, and also pick out areas for missing core data. So before I move on, there's also you can also maximize data value in your data. I mentioned earlier that many companies, we have data that has been trapped in formats that cannot be like legacy data, valuable information that have been trapped in old formats that we cannot really access. This is what like a specialty of my team in my company, where we pick out all those your old logs, all those your scanned PDFs, your core images, your thin section images. We pass it through our pipelines, do different document segment analysis. So you can say, okay, this is a table in a document. You can get a PDF, for example, a scanned PDF. You can identify the different pages within a document. You could do text search. You could say, okay, within this document, I have XYZ tables, I have XYZ paragraphs. And you can now extract this information from these different documents and convert, maybe like turn it into a structured format and store it in database where a geoscientist, for example, can easily extract this information, discover. So instead of spending time to search for information on this dash UI, for example, you can just go search, for example, a particular discipline, or you can, let's say, filter based on a particular field or particular well to see what are the information contained within that well, what are the data. So everything, so you have all your data in the same data verse where, for example, a reservoir engineering data is connected to a geology data, is connected to a sedimentology data. You can easily link things together rather than having things in silos. So now we've talked about different applications, we've talked about different things. So what are the tools you need to achieve this? So you could start with basic Excel, Power BI, Tableau, Aperture Spark. These are just some traditional data analysis things you can start with. So these are mainly for data analysis to visualize what you have. And when you want to start going into more deep data science things, you start looking at programming languages like R, using R Studio, or you want to use Python using some integrated development environment like Google Colab, like Visual Studio Code, Jupyter Notebook, or PyCharm, depending on do the same thing, just depends on what you prefer. Then you also talk about some data science libraries. So if you want to start using data science with Python, so you want to focus on some libraries like NumPy, Numeric Python, Pandas, Matplotlib, Seaborn, GeoPandas. These are some data science libraries that you need to learn if you want to start using Python for data analysis and also for geo data analysis. Then if you want to start looking at machine learning, you have to start looking at things like TensorFlow, like Scikit-learn, PyTorch, Keras. These are some images, so these are some libraries, for example, that you can use to train models, to get machine learning algorithms to help you make predictions. Then for I talked about database management and database querying. For things like this, you want to use SQL, and you can use it on the Oracle or MySQL or Postgres. These are different instances where you can run your SQL queries. But as a beginner, I advise people you can start with if you don't want to, because a lot of people's programming scares them. So if you don't want to do that, you can just go with Power BI, Tableau, and let's start from there. That will be a good starting point to understand the data analysis techniques. Then you can now start going into more programming things. Then I just want to touch on some soft skills, like data analysis. It's not just about technical skills. You also have some soft skills that you need to generate, that you need to have, for example, problem solving skills. That's very important because a lot of times you're going to have some problems. You could have problems with your code. You'll need to be able to trace the problem. I'll trace the bug in your code or show what the problem is, why is something not working. You should have that skill. Then curiosity. In most cases, data scientists are really curious people. Sometimes I look at myself and look at some things I've done. It's just about curiosity. I just want to know why is the earth green, or why is this data. Sometimes when you do your data analysis, it confirms your assumption. Sometimes it negates your assumption. So if you have an assumption, why is X, Y, Z this? You want to start getting data that would help you make that to answer those questions or make that decisions. You also be an analytical thinker. So you should also know how to think analytically. Also have to pay attention to details. It's very important. Know how to cross your I's, dot your T's, and let's pay attention to the little. For people that code, for example, if you miss a comma in your code or you miss like a closing bracket, it can make your code not run. It can introduce errors in your code. So you should be able to identify those little errors within your code. Communication is also very important. It's one thing to do a very great job, but it's another thing to communicate. And in most cases, you work with different teams. For example, I work with data engineers, I work with software developers. So you should be able to communicate what you want and just have that effective communication, and also storytelling skills. In some cases, you have to kind of make presentation or communicate your finding to non-technical stakeholders. So you should be able to tell the story of the technicality in a less technical way so that people can understand. So you should be able to tell them interesting stories so that you don't lose them. So you have to develop that skills, and also you have to be adaptable. So the technology industry is changing. You should adapt. For example, you can go from company X to company Y, and the tools they use could be slightly different. So you should be able to adapt, or the working environment might be different. So you should be able to adapt to this changing environment. Okay. So I just want to touch on the roadmap. So if you want to learn the skills, where do you go? So I mentioned earlier, Excel, Power BI, Tableau. It could be where you could start from. You could pick up any of them, and it's a good pointer to start. Then you can now start focusing on more technical things like learning Python. I recommend that people learn Python as programming because it's easy to learn. It has easy syntax. It's like your normal human language. I think it's one of the easiest programming language to learn, to be honest. And you start with the Python basics, then you can start talking about statistics, probability, median, measures of central tendency, measures of variability. Just understand, you don't have to know the y, the x, no complex mathematics. Start with the simple, at least if you know, okay, what is a mean? How do I calculate a mean? And in most cases, you don't need to know how to calculate a mean because there are different functions in Python that can generate that. But you should understand, what does a mean tell you? If you have median, how does a mean differ from a median? If I want to calculate standard deviation, in what cases do I use standard deviation, or in what cases do I use standard deviation or use variance? So things like that, measures of central. You just need to have an understanding of those at least fundamental terms. You don't have to get complex concepts because it can really get confusing. Start with the basics, then you can now move on to some more advanced Python things, like learning Python functions. So for basic Python, for example, you want to learn Python data types, Python variables, different data structures. Then you want to start going into advanced Python. You want to start learning things like flow, control flows, like functions, for loop, if statement, how to create a function. Then you can look at different libraries like pandas, SQL, not SQL, pandas, NumPy, matplotlib. So just some more advanced concepts. Then from there, you can now start picking up SQL basics, looking how do I query a database, how do I select all from XYZ table to get the data you want. So like I said, you don't need to go learn SQL that a data engineer will use. So you want to learn how to query database. Then also start doing data visualization. Yes, I discovered XYZ. How do I visualize this data? How do I communicate? They'll tell you a picture says more than 1,000 words. So you have to be able to create good pictures, good visuals. They talk about data transformation. How do you manipulate your data? How do you remove erroneous data? How do you spot erroneous data? How do you take it out? How do you treat it? How do you maybe change data from one format to another? That's some of the data transformation you start looking at. How do you scale your data, or how do you normalize your data? Then from there, you can now start applying machine learning models. You want to know, is it classification? Is it a regression problem? Do I have to apply unsupervised learning? Things like that. Then you can now start learning, doing some deployment, that is deploying your machine learning when you think is good enough. Okay, then these are some, because this is one of the questions I get from a lot of people. So I know, where do I start from? Where do I get these resources? There are lots of resources online that you can start with. So you can go check Udemy, Coursera, YouTube. Like I mentioned, I have my YouTube channel, so you can scan this QR code to take you to my YouTube channel. You have W3 Schools Data Camp. These are like, and on these platforms, there are some free materials and there are some paid materials. I tell people, go for the free one first. Don't jump to pay money. And let's start with the free courses to test your enthusiasm, to test your to see if it's something you can do. Then you can now start coming. When you've at least understood the basics, you can now start going to start paying money to maybe gain certifications. And some platforms that you like, I think you can benefit from, will be GitHub, Stack Overflow, and Cargo. So you could just go type question. For example, you're trying to do something and it's not working. You just go type on Stack Overflow or GitHub. You see people have had the same problems before. You can see how they solve the solutions, things like that. So these are good platforms where you can register on. You can build portfolio on there to showcase what you're doing and also just get feedback generally. I think that's all what I would say. I'll just conclude by saying data scientists and machine learning engineers are not replacement for humans or for geoscientists. So they just help you focus on make you apply your knowledge to more efficient things. Then you can embrace the power of data science and machine learning to complement your geoscience skills. The world is changing, technology is taking over, so it's not enough to just have geoscience skills. It's good to have other additional skills that would help you. And yes, so with these tools you can make more applications or make new possibilities. It just helps you keep breaking the possibilities, keep shifting the boundaries and making impact. And I just want to say, most of the times when you start doing this, you just have to stay curious. You just have to keep learning. As humans, you never stop learning. So you just have to keep learning, keep pushing yourself, keep staying curious, and be determined. Sometimes these things don't come easily. You have to be determined to push through. And one tip I tell people, if you want to learn a new skill, start into something that you're passionate about. Don't just do it. If you, for example, you're passionate about the world. If you're passionate about politics, for example, start with politics data, analyzing. So if you like sport, so just tie it to something that interests you, because sometimes it can really be discouraging. But if it's something that you've tied it to something that is of interest to you, you bring out that excitement, and when you start seeing results, you keep pushing and pushing.